So for last two lectures, we are looking at the problem of regression. And this is the problem setting of formalization of regression problem. We are given a set of real valued instances, or this is our feature vector, and we want to find a target function that maps inputs to outputs. So again, if you are given n training examples, these examples can be denoted by like this. So x is a feature vector, y is the output of that feature vector, and x example y is, for example, in a given example image, x's are experience, and based on experience, we are trying to predict salary of a person. So this is, as salary is a real valued output, there is no notion of predefined number of classes. So this is a problem of regression. In classes, in classification problem, we have predefined number of classes, but in regression, output is real value. And regression is about finding a function that maps inputs to output. So if we are given one variable, this is univariate regression problem. So we are trying to fit a linear function or a line that minimizes the error, or which is as close as possible to all the data points, right? And we can use calculus to find this best fit line using least square errors. So this is what we have done in last lecture as well. And here I give you intuition of different parameters of line, like how these parameters affect on the line. And I told you before in my last lecture as well, like hypothesis in textbooks is usually denoted by h of theta, and parameters, this theta are given as theta 0 and theta 1. Here I have denoted theta 0 with C and theta 1 with M for intuitive purposes, because we already know that equation of line is mx plus C, and where C is y-intercept and M is slope of the line. So here I have given you few examples just to give you intuitive example. If there is no slope, line is parallel to x-axis and C is y-intercept, so its y-intercept is 1.5, so line start from over here. So this is like constant line. A constant line means output remains same regardless of the input. If C equal to 0, C equal to 0 means line passes through origin, and M is again the slope. And if C equal to 1, it means y-intercept is at 1 and slope is 0.5, right? So it's very intuitive to know how these parameters can affect a line that we are trying to predict. Then we looked at this sum of the loss function, which we have done earlier. We discussed briefly about 0-1 loss, sum of squared loss, and absolute loss. But we use sum of squared loss because of mathematical reasons, because this sum of squared loss or squared error function is convex and easy to derivate. And because of this nice mathematical properties, we use this function in regression. Then I showed you like how we can find maximum of a function if there is only one variable, which is, I give you example of C. We can just differentiate this function and make it equal to 0 according to Fermat's algorithm, and we can solve for C to find a value that minimizes this function or extremum of this function. So here the example I showed you in my last lecture as well. So this is sum of squared error. Yi is actual output and C is, let's say, predicted output. And if we want to find C that minimizes this loss function or a line, or it finds the line with best fit line, we can just differentiate this function with respect to C, because this is the only variable in this function, and we can make it equal to 0 like this. So first we differentiate, then make it equal to 0, then we'll solve for C to find value of C that minimizes this loss function. And this is the main aim of regression, to find minimum or to minimize this loss function. And if when we are trying to find the constant line, this is very interesting example. It comes out to be a mean value. So as I told you before, if you are given this kind of a data set, and you're trying to find a line, a constant line that best describes this data, this would be a mean value. So let's say if this is 30Ks or 30,000, like given the example, and 0, and probably mean values around here 25. So this, according to this solution, this would be line or the mean line. So regardless of the input, the output remains the average value of all the data points. And in the same way, we can find value for m because we have two parameters m and c. So in previous example, we solve for c and we make it equal to 0. Now we can solve for m and make c equal to 0, and c equal to 0 means line passing through origin. So we are just trying to find a line which passes through origin. It could be line like this or something like this or this or this. So all the possible values, all the possible lines. And again, we can just write this loss function. So y is actual value, mxi or m is the parameter. So we can differentiate with respect to m, make it equal to 0 and find the value of m or slope of a line, which comes out to be like this. You can calculate manually as well, like I did in this example. If this is the data set, this would be the constant line without any slope, and this line would be passing through region. So this actually gives very nice results. So this is just the intuition of regression. Then we, in last lecture, we discussed cost functions. So this is the cost function. This is how we can describe the cost function for regression. So y hat is predicted value or value given by our hypothesis, and y is actual value given in the data set, and n is the total number of samples or examples in the data set. And we write 1 over 2n for mathematical convenience. As I showed you last time, when you take derivative of this function, this 2 crosses out. So we just, and this is a scalar, so it doesn't make any mathematical difference on optimization problem. So we are trying to minimize or find values of m and c that minimizes this cost function. So this is like a complete formalization of regression problem for one variable regression problem or univariate regression problem. So this is the hypothesis we took. These are the parameters that we are trying to find that minimizes the cost function. This is the cost function, and goal is to find values of m and c that minimizes value of j, a cost function which is given by this. And then before solving this optimization problem, I gave you few visualizations. So at least you will understand how this function looks like in 2D and 3D. This was the problem I solved initially, and that was the thing I wanted to show you. So this is the cost function given in 2D. So 2D means there is only one parameter m, and this is the cost function based on this m parameter, and this is like a bowl shape function, and this is actually convex function, and that's why we took sum of squared error function. And I visualize this cost function in 3D as well. So 3D means there are two parameters, m and c, and third dimension is the cost associated with these two parameters. And I showed you, like, if you plot this function in 3D, you will have this kind of a function. And if you remember, I showed you in MATLAB as well. Is this window visible to you guys?
जी sir.
Right. So this is a cost function which we are discussing in 3D. So you can see it has a very nice symmetrical bowl shape, and there is only one local minima or extremum of a function, right? And that's what we are trying to find automatically, how to find values of m and c, which minimizes this cost function, right? I will show you again. So this was the cost function in 3D, and now the thing is we have a cost function, but we want to find values automatically that minimizes this cost function. And for that, we started looking at gradient descent algorithm. Gradient descent algorithm is used a lot in machine learning in different for different optimization problem, and in regression it is also used. So the idea is if you have different weights gradient descent will find a value that minimizes that cost function. So you could define different cost function. You can apply gradient descent algorithm, and it will find minimum values. It will find values of those weights which minimizes that cost function j, which is given by j. So this was kind of pseudocode I showed you for gradient descent algorithm, and the main crux of gradient, as it is gradient descent, gradient is a derivative. We can find gradient using derivative. So we can just, if you look at this pseudocode of gradient descent algorithm, it initializes all the weights by some random value. Here right now we are working only with 2 parameters, but it could have 10 parameters, 20 parameters, doesn't matter. The second step is to calculate gradient of function. Here we are using sum of squared error, and based on those gradients we'll adjust weights of parameters, and we keep on doing it till convergence. Right? So it's very intuitive algorithm. So this is how this conversion goes like. I'm showing you in MATLAB again. So let's say gradient, you start using these values m and c. I believe this is a good visualization for you to understand. And right now, algorithm is over here with different values m and c, but the aim is to find values of m and c which minimizes this cost function. So it takes step, like you can see, it takes step downhill. So this is kind of a hill, and gradient descent algorithm moves in a direction where gradient takes, right, where gradient is pointing, right? So based on that gradient, it changes its weight so that it can find minimum value of this cost function. Right now, if you remember, last time we discussed alpha or learning rate as well, and I will show you in next slide as well. This alpha dictates how long this step would be. So algorithm is stops here. It's if you think like if it's a person and looking downhill, and idea of algorithm is to find or to move in a direction with the steepest gradient possible, right? So it takes step in that direction in order to find valley of that function to touch the ground, right? So you can see it is taking like baby steps and moving towards minimum value. Right? So it's very intuitive and interesting to see how gradient algorithm moves in this 3D ball shape function, right? It is nicely converging. So this is how this gradient descent algorithm works. If you want to just see in different directions, so you can see, if you see 2D, it's very intuitive as well. So algorithm is trying to find this middle square in the function, and up till now it's reached over here. So if you keep on moving, it's moving in the same direction. And you can see when gradient are it's on the steepy side of the hill, the gradient actually dictates alpha as well, and I will discuss you. But as we are approaching valley, the steps are getting smaller. So it's kind of adaptive as well in gradient descent, because alpha gets multiplied by the gradient. Here gradient is more, so when you multiply alpha, the steps are bit bigger. So alpha remains same, but still steps are bit bigger. But as you're approaching valley, steps are getting smaller and smaller because gradient is very small. You can see the here gradient is very small, right? So this is very nice visualization to see how gradient descent algorithm is trying to reach minimum of cost function, right? And any problem, any issue, any query up till now?
नहीं सर, लाइक सर जो मिनिमम पॉइंट होगा वो बेसिकली एम और सी की वैल्यूज होंगी जो हमें मिनिमम कॉस्ट फंक्शन देगा, राइट?
Exactly. So it is trying to find values of m and c that minimizes that cost function, because cost function is based on m and c.
राइट सर.
Right. So it is changing values. Sometime I call them weights, but these are values of M and C or weights of parameters, and you are changing weights of parameter to minimize this cost function. And you can just think, when you change M and C, line is changing. Remember, I showed you in the example when you change M and C, this line changes. Either it's y intercept change or gradient changes. So these are different hypotheses it's creating, and it is adjusting that hypothesis so that it finds best fit line. It's very intuitive if you think in this manner, right? So
Right,
mathematically
right.
this. Right, okay. Mathematically, a gradient descent algorithm is written like this. So I have written over here weights. An example, these weights, WIs are M and C, right? So here I have written WI, so WI is also M and C, and you differentiate. So this is like a weight update rule for gradient. It says that update this weight, or let's say if it is M, so M equal to M minus this term, right? And when you partial derivative with respect to M and J of M and C. So that would make more sense to you guys now. So this is like M equal to M minus alpha. Alpha is learning rate, and I will explain in next slide as well what is the effect of alpha. But this is the important term. The derivative with respect to M of a function, which dictates where to move from steep hill towards the ground, right? So as I showed you in this example, this is the gradient. The gradient is directing where to move on this 3D ball shape function. Okay, let me move forward. This so this is how this algorithm converges. Let's say so alpha is the learning rate, and let's say algorithm is over here. And when you take a derivative, derivative would be positive because this is the derivative of this line, right? This is the derivative of this line, and as derivative is positive, so this would be m equal to m minus alpha into some positive number. So it means that value of m has to reduce in order to move in this direction, right? Because right now m is somewhere over here and it has to decrease its value to reach minimum value. So this is what this gradient is directing or telling algorithm what to do. And vice versa, if m is over here and if you take a derivative in this direction, derivative would be in this direction and this derivative is negative, and when you write m equal to m minus alpha into some negative number, so this negative and negative make it positive, and which tells that m has to be increased or value of m has to be added with some number which is equal to alpha into gradient, and which dictates that m is right now probably at minus 80. It means that m has to move, value of m has to be increased in order to reach global minimum over here, right? So this is main concept or intuition of gradient descent algorithm. And this is effect of alpha I discussed in my last class. So let's say we start over here, and if alpha is very small, algorithm will take baby steps because this is a scalar which multiplies, scalar that multiplies with the gradient value, which is either added or subtracted. So alpha dictates how long this step would be in global minimum direction. So if alpha is very small, it will take baby steps like this. Probably it will take 100 or 200 steps for a given example to reach to global minima. But let's say if you take alpha too large, what would happen? So if algorithm is over here, after one step, it could jump over here. Then next iteration, it could jump over here. Next iteration, it could jump over here. So it totally misses global minima. So if you take alpha very large, it might happen that algorithm doesn't converge or it diverges. So this is very bad. And the idea is to find alpha which is not very small or not very large. So this is a parameter that is Sometimes people have worked, there are a lot of literature, what should be the good value of alpha, but this is the idea of alpha, right? So you should understand if algorithm is not converging, this could be the problem. And this is very nice illustration I took from Stanford's course on convolutional neural networks, which shows effect of learning rate or alpha. So if alpha is very high, like in my last example I showed you, algorithm could diverge. So this is the example of alpha very large. And if you take good alpha initially or algorithm is tuned with good alpha, it will smoothly converge to global minima like over here. Right. If learning rate is not very high but still high, it could find itself in local minima. So this is like illustration to show you effect of alpha or learning rate or on convergence of an algorithm. Now today we'll see how we can use gradient descent method to find optimal parameters of a line for regression. So again, this is our cost function, right? We all remember this. Y hat is predicted value or value given by h of theta, if you are thinking in terms of hypothesis like this, and y is actual value. And 1 over 2, 2 is, we use this one for mathematical convenience because we'll take derivatives. And this 2 and 2 would cancel out. Right? So we are working with this h of theta is given by mx plus c because we are working with this equation, right? Or you can just say theta 1 m plus theta 0 if you are comfortable with this. And this is the algorithm of gradient descent algorithm, right? Which we have discussed just now. And we want to apply gradient descent algorithm that to minimize cost j, or we are trying to find automatically values of m and c using gradient descent method in order to minimize this cost function. So this is the whole intuition of using gradient descent algorithm over here. So this is our cost function, and remember we are derivating it, this cost function, right? So this is how this derivatives could be done. I will briefly explain, and if you're not sure, I'll encourage you to do it on your copies because this is very easy and you have done calculus course. This is just calculation of derivatives, nothing else. So y is given by mx plus c. I am just putting values of y hat mx plus c, and remember I have written over here wi, but there is no w in our function, but this w is just to show that these are different weights of parameter weights, and our parameters in this function are m and c. So let's say for this function this wi would have two cases. Once wi would be equal to m, second wi would be equal to c. So these are two different parameters we are trying to predict values, right? So we have to do partial derivative with respect to these two parameters. And partial derivative, just to let you know, partial derivative is where you will just differentiate function with respect to one variable, making others constant in order to find value of that function, value of that parameter for a function, right? This is just a reminder for you, right? So if you solve when wi equal to c, let's say you are taking derivative, let's say you are taking derivative with respect to c of this function. Here this 2 would come down over here, so this 2 would cancel, so 2 and 2 would cancel, we will have to be 1 over n, right? And this function remains same because this is initial step, and then you'll differentiate inner side, and you are differentiating with respect to c, making others constant, and the differentiation of c with respect to c would be equal to 1. So this remains same, there is no change in there would be no change. So I've just written back same thing, and y hat is mxi plus c, right? So this 2 just cancel out, and once you differentiate with respect to c, we will get this function. And the second case is when wi is equal to m, or here I have written wj. Just to let you know that this is different parameter. So once you differentiate with respect to m, again this two cancel out, you write this whole thing, and then you differentiate inner function with respect to m, and when you differentiate this with respect to m, making c would be constant now this time, and when you differentiate mxi with respect to m, you will get xi only, right? So this is a partial derivative with respect to m. Any query in this solution? Any query right now?
No, sir.
Is this clear? I encourage you to solve on your notebooks just to see if I'm not making any mistake. So just for double check, I'll encourage you to take derivative of this function with respect to m and with respect to c, right? So this is how this partial derivatives can be calculated easily. And now you will understand why I have took 1 over 2n initially. So 2 cancels out, right? Now this equation is more intuitive and makes more sense. Now we plug back equation 14 and 15. So these two are our derivative functions or answer of derivatives. And we plug back these two into gradient descent algorithm, which is given by this, right? So this is weight update rule of gradient descent algorithm for univariate regression using gradient descent. So we have two parameters C and M, and you remember this is if you just replace value of C over here, so C equal to C minus alpha, and then what we calculated in equation 14, which is 1 over n summation I goes from 1 to n, this should be n, this should be I, 1. So I goes from 1 to n, y hat minus y hat minus y, right? So this is update rule, and you can update C parameter using this value. And for m, there is additional term which is xi, multiple of xi, because once we derivate this function with respect to m, we get this xi back. Right? So this is very easy update rule, and you can update values of C and M to find best fit line using this calculation. Any query up till now? Any query?
सर तो इस अपडेट टूल से हम लोग ये कैसे वेरीफाई करेंगे कि हमारे पास जो वैल्यूज एम और सी की आई हैं वो मिनिमम कॉस्ट फंक्शन के लिए हैं?
Okay. So this says repeat until convergence. So this is inside a loop, and you need to define a rule for convergence. One of the easiest rule of convergence is once you find that old C is equal to new C, which means there is no update or algorithm has reached minimum value. So once algorithm stops changing values of parameters, then it means algorithm has converged to global minima. So this is one of the easiest convergence rule. But in practical examples, people use a specific number of iterations, and after that they stop. Let's say you run a loop for 1,000 times, and you update this value of C and M 1,000 times, and you just say, okay, this is approximately we have reached minimum value. So there are different criterias for convergence, but these two are usually used in literature. You can find in the book as well, right?
राइट सर.
Okay. So up till now we were discussing univariate or a line with one variable with one parameter. But let's say if you are given d-dimensional feature vector, which we can just write like this. So if you have different parameters and you want to use this gradient descent algorithm to find best fit line or surface for a given data point. I cannot visualize this after 3D, but let's say if you are given, I don't know, 4 or 6 dimension feature vector, we don't have that visualization power to visualize more than 3D. but we can use the same gradient descent method and the intuition remains same. Remember, we updated C using this thing, and here this is assignment. So it means that assign this value into this variable. Right? So this is assignment operator, and there is an error. This I should be from 1 to n. Right. So remember, when you differentiate with respect to theta naught or c, we'll get back this one. And after that, once you differentiate with respect to theta 1, we'll get this thing back. Multiply by amount theta 1 was getting multiplied, right? So it previously it was mxi. So m and m becomes 1 when you differentiate m with respect to m, and you get back this scalar back. So if you have different parameters, the idea remains same. If you have theta 2, theta 3, theta 4, you will get back the same thing, multiply by xi2, xi3, xi4. So this is very intuitive. If you think that you can just use gradient descent algorithm if you have d-dimensional parameters, or if you have 10 parameters or 20 parameters, this gradient descent algorithm will remain same. Only just this derivation should be in your mind, like how you can use it, right? Any query up till now?
No, sir.
Okay. So it's very interesting property of gradient descent that I want to discuss with you guys. Let's say this is example I took from Andrew Ng's class. This is very intuitive, and I took this example from his class. Let's say you start gradient descent algorithm over here. So gradient descent algorithm will look where is the steepest gradient to reach a valley, and it will just look all around it, and it will find best possible step and take that step like this, right? And if algorithm reaches over here, if algorithm gets initialized over here. But let's say this algorithm, let's say gets initialized here. This is just few steps on the right from the initial starting point. But then the steepest gradient changes in different direction. It would find a different local minimum. So based on initialization of parameters, this gradient descent algorithm can find different answers. Right? So I just wanted to tell that if your function has a different local minima based on initialization of weights, gradient descent algorithm can converge on different uh, uh, values of parameters, right?
Right, sir.
This is the property of gradient descent. And just few variants of gradient descent, if you just read in the book, you will find different variations of gradient descent algorithm. Gradient descent is used a lot in machine learning. It is also used in neural network optimization problem. There are different variations of gradient descent. The gradient descent algorithm which we just discussed before is called batch gradient descent, right? And most common, this is the most common used gradient descent. So batch gradient descent is when we sum up all over all examples on each iteration when performing update. So batch gradient descent algorithm actually updates after running it over all the examples in a given data set. So let's say if there are 100 examples in the data set, weight values will be updated after looking all 100 examples. So advantage of this batch gradient descent is fixed learning rate. You don't need to change this learning rate. It has straight trajectory. I will discuss what I mean by straight trajectory. Don't get confused with this. It has unbiased estimation of gradient, and it can benefit from vectorization. Vectorization is parallelization of your code. So things can be done in parallel. A lot of things can be done in parallel. But disadvantage is as update is after seeing all the examples, it means that it's very slow, especially for large data set. Let's say if you have 100,000 examples and you are updating after looking all 100,000 examples. So for one update, it means that all 100,000 example has to be seen by the algorithm. So it means it converges very slow. And each step of learning happen after going through examples. Think of outliers in the data set. So if you have outliers in the data set, the weight would be updated considering that outlier as well. So these are some of the problems associated with batch gradient descent. Just opposite of batch gradient descent is stochastic gradient descent. And stochastic actually updates after seeing each example. So instead of going through all examples, stochastic gradient descent perform parameter update on each example. So let's say if you have 100 examples in your data set, it will update after looking just one example. So after looking just one example, weights would be updated. So advantage is easier to fit in the memory because your just algorithm is looking one example at a time. It is computationally very fast because updates are happening after seeing just one example. But due to frequent update, the step taken toward minima of the loss cost function have oscillations, which can help getting out of local minima. I'll explain this thing in next slide. And disadvantage is due to frequent updates, the step taken towards minima very noisy. I will explain this probably. Let me explain this over here. So this is the contour plot. Do you know what is contour plots?
सर देखे तो है contour plots लेकिन अभी exactly remember नहीं कर सकता कि क्या plot
Okay, I'll
लेकिन हाँ
just briefly explain this contour plot, and I'll encourage you to see this contour plots in literature because this makes a lot of sense when you're looking this convergence of optimization problem. So this contour plot means on this contour value of j remains same. So different values of W1 and W2, you can just these are changing, but cost of that function of or that loss function will remain same. So let's say if j value of cost function is x, it remains same for different values of W1 and W2 in this contour. Now for this, let's say x2 would be cost for different values in W1 and W2. So cost remains same on the contours. This is the idea. And you see this light blue line corresponds to batch gradient descent algorithm, and batch means you update after looking all the examples. So this is very smooth. After looking an example, algorithm updates W in this direction, like in the local minima very smoothly. But next I showed you stochastic gradient descent, and we were discussing that it oscillates a lot, and this is like how it oscillates. So let's say algorithm starts over here, it takes step in this direction after looking one example, then another example, it changed direction in this, then goes back upward, then again downwards. So it is like going in this direction, like something like this to reach global minima. On the other hand, batch gradient descent just do this, but it's very slow. And the middle point for this two batch gradient descent and stochastic gradient descent or trade-off is mini batch gradient descent algorithm, which is given in green, which oscillates less than stochastic gradient descent algorithm, but oscillates more than batch gradient descent algorithm. And in mini batch gradient descent algorithm, instead of updating after every example, it updates, let's say, after n example. So if you have 100 examples, algorithm makes mini batches of, let's say, 20 example. So it doesn't wait for the whole data set to update, or nor it updates after every example, but it makes strata or different layers. Like which we did for k-fold cross validation, we divided into different k-folds the same training data or validation data. So here again, this data set is divided into different portions, and after each portion is run, algorithm updates weight parameters. So this is like a trade-off between batch gradient descent and stochastic gradient descent. So it has properties of both. So any issue or any query up till now?
No, sir.
Okay, so this was the intuition of gradient descent algorithm for different parameters. We looked at issues associated with gradient descent algorithm. We saw multivariable as well. I think I have few. You can just code this linear regression algorithm in Python using sklearn, as I told you before. If you don't want to code a gradient descent algorithm yourself, it's already coded. You can use it to verify different ideas, different concepts. So this is the same example which I showed you earlier, and I use sklearn library to find best fit line, and you can see this is giving quite good examples. So this is the training set, and on test set you can see these points were not included. These 4 points were not included in training, but our best fit line is quite near to those points and giving quite good, will give quite good results. So inductive bias of linear regression algorithm or supposition of linear regression algorithm is that relationship between attribute x and y is linear because it's linear regression, and the goal is to minimize sum of squared error. So this is inductive bias of linear regression. Okay, I propose to stop over here.